So today we're moving into the last thing that we're going to do for databases, which is the physical design of the database down at the level of files. So we've seen the user level thus far, where the user is manipulating the database. We've seen the design level where the designer is creating the data model, which gets translated into the DDL. And finally, there's a mapping down to the physical files themselves. So this was with the user, the direct manipulation language. Then with the design, even though we were talking about the ER diagrams and normalization, that data model is what gets translated into a DDL or is realized via a DDL. And the last thing that you need to do is you need to map your relations into physical files. And the second goal of physical design is to select indices to aid the query processor in allowing it to return information as efficiently as possible. And not sure how much, so just again throw this question out. So how much have you seen, or in like 360 or 302 or some other course, talked about emphasizing the speed of disk access as opposed to the speed of memory? That is, where you talk about a process being what we called I/O bound rather than CPU bound. Have you heard those topics? Some of you had, some of you haven't. Okay. So there is kind of two notions, one of a process being I/O bound, and the other notion is of a process being CPU bound. A I/O bound process is one whose execution time is constrained by its access to disk. That is, it's spending most of its time waiting for disk accesses. So execution time is constrained by disk accesses. Okay, and I'm going to say i.e., a lot of the time, much of the time, the process is waiting on a disk access. Okay, in contrast, with CPU bound, execution is constrained by the speed of the CPU. So it is generally executing without any need for I/O. Okay, so most of the execution does not depend on I/O. So physics simulations are good examples of CPU-bound programs. They may collect some input at the beginning, but once they've got that input, they simply are executing CPU cycles, and they're not really doing much with the file system. By definition, databases are I/O bound. Programs that are interacting with databases, for the most part, are waiting on disk accesses. And disk accesses are much slower than memory accesses. Okay, that's why if you're stuck with an old computer like I was when this computer was in the shop, and you don't have enough RAM to hold your processes. They get shoved out to virtual memory, and when the CPU goes to execute an instruction, it turns out that the piece of code you need is in virtual memory on the disk, and instead of being able to quickly retrieve it from RAM, it's retrieving it from the disk, and you hear this awful whirring of your disk drive, and your program seems to be running like a snail. Okay? Well, to give you an idea, the access times for disks are what you see here. I know these are 2014 figures. They're not going to be hugely different this fall. So you buy a high-end disk, it's going to be about 3 milliseconds for a disk access. For your average desktop, it's going to be about 9 milliseconds. And on a mobile device or a laptop, the average access is going to be about 12 milliseconds. If you're lucky enough to be on a solid-state device, the access times go down considerably. Then it's less than 1/10 of a millisecond. And we'll talk about seek time in a moment. But the access times for solid-state devices are clearly much faster, about 30 times faster than even a high-end disk. But the point of this is that database programs that interact with a database, the constraint on them is the disk, and hence what you're trying to do is minimize the number of disk accesses. You're willing to trade increased CPU usage for fewer disk accesses. So you're willing to be more inefficient with the CPU, or alternatively, you're willing to explore several different possible ways to retrieve information from the disk before you commit to a specific query plan. A query plan is the kind of steps that you take in order to satisfy a query. For example, if you're doing a select and a join, do you do the select first and then the join, or do you do the join first and then the select? Okay, most query plans say do the select first to reduce the number of tuples that are involved in the join. Okay, so if you have not, some of you have seen what a disk looks like, some of you have not. So I kind of have to make sure everyone's on the same page. So basically, disks look like what you might think, a disk. Okay, they have what are called tracks on them, and the data is stored on tracks. Okay, the tracks are divided into units themselves that are called blocks. The fundamental unit of information that is read from a disk is a block. So when you access a tuple in a relation, it doesn't just read that tuple, it actually locates the block on disk that contains that tuple and reads the entire block. Okay? Block sizes vary. I believe in Unix they typically are 4096 bytes, but it can vary from system to system. As an example, if your tuples are 100 bytes, then you could fit 40 tuples onto a block. So when you go and actually retrieve a tuple, you actually end up retrieving about 40 tuples. Okay? Kill. Someone needs to kill that. Sorry. I think it's you, Anna. Thank you. It's okay. I can't concentrate with it, though. Okay. So you are reading So the goal is to minimize the number of blocks that you end up reading. For example, if you have a query and you have, say, 30 tuples that satisfy the query, but those 30 tuples, say, are only on 5 blocks, then your goal is to only read those 5 blocks. You're not trying to read every block in the relation. Let's say that the entire relation takes up 100 blocks. Okay, your goal is to just read those 5 blocks, not all 100 blocks. Because reading 100 blocks is going to substantially slow down your program. Okay? Now, when you access a disk, there are 2 components to the access time. The first is called the seek time. So there's an arm. So these disks are actually organized as a stack of platters. So this is just a single disk, but an actual hard drive is a stack of platters. There is a read arm in this stack. Okay, so this is your stack of platters right here. There's a read arm that is going back and forth to the various tracks. Okay, so the time it takes for this read arm to make it out to the track that contains your block is called the seek time. So back here, seek time is the time to move the mechanical read-write arm to the appropriate track. Okay, but there's then a second element to it, which is that once you reach the appropriate track, there's no guarantee that the appropriate block is underneath it. So for example, when you get to the arm comes out, maybe the arm is fixed right here, but when you actually get out there, your block is over here. So the block has to rotate under the read-write arm, and that's called rotational latency. So that's the time for the disk to rotate the correct track under the read-write arm. So rotational latency, the time for the appropriate sector or block. There it was sector, but block is a synonym of track to rotate under the read-write arm. Okay? Then, so that's one element of access time. That's the time required to physically get the appropriate block under the read-write arm. But there's a second element, which is how fast that data can then be streamed back to the computer. Okay, so that has to do with how fast the disk is spinning. The faster it spins, the faster you can read information off of that block. It depends on things like the system bus. So that's what point 4 here is referring to, is the transfer rate. That is how much data you can move if you just are constantly reading. So if the arm is just there and you start reading, how much data can you move in a single second? So high-end enterprise-grade disk drives can move about 140 megabytes per second for both reads and writes. Okay, and it goes down a little bit for desktops and mobile devices. I don't have those numbers actually at my fingertips. Okay, so the second type of secondary memory where a database might be stored is solid-state memory. How many of you have solid-state memory in your machines? Okay, so about half of you. Sure, when you first started using them, you were impressed at how much faster they seemed to be than the hard disk drive. And as I just said, there's a good reason for that. Their time to get to the right piece of information is less than 1/10 of a millisecond, so 30 times faster than even a high-end disk drive. Their transfer rates on reads are between 100 to 600 megabytes per second. It's a big variation. So your laptops are slower. They have cheaper solid-state memory. You can pay a lot more and get solid-state memory that's high quality and will transfer at 600 megabytes per second. In your laptops and mobile devices, it's probably closer to 100. Okay? And the write times for higher end SSDs are roughly the same as the read times, but for cheaper memories, like what you probably have in your laptops and mobile devices, the writes are about 10 times slower than the read rates. And don't ask me why. I'm not a electrical engineer or a physicist, so I just know that that's the case. Okay? So the bottom line is that once even 0.1 millisecond isn't exactly blinding compared with access times to cache and to RAM. So even my machine, my 5-year-old machine, actually was solid-state memory, and as exasperated as I appeared in class with it, it would have been a lot worse if that machine had been running an actual disk drive. Okay, so you could see, even from how slow it was in class and the problems I had with it, that solid-state memory was not the ideal solution. So we are trying to do everything we can when we map our relations to the physical files to do so in a way that's going to allow the query optimizer to minimize the number of disk accesses. Okay? Query optimizer is much like a compiler. A compiler translates a high-end source down to machine code and may do some optimization. A query optimizer takes a SQL query, translates it into a set of operations on the file system, and tries to optimize it. Okay? So, there are 3 common organizations for files. Heaps, which are not your, remember what they were in 140 and 302? Okay, they're not those heaps. Okay, they are unordered files. They're just sequential files, no ordering on them. Okay, what that means is they're not sorted according to some key or ordered according to some key. So I'll say not unordered means not ordered on any field. Okay, and you'll see that I'm going to start using the word field rather than attribute or column, because in the world of file systems, we talk about files rather than relations. We talk about fields rather than attributes. Okay? We talk about records rather than tuples. You're going to hear me going back and forth, but when you hear me use the word field, what I mean is an attribute. When you hear me use the word file, I mean relation. And when you hear me use the term record, I mean tuple. So you're going to hear me go back and forth between those terms. Okay, the next one is a B+ tree. I suspect about half of you have seen a B+ tree, or have all of you seen a B+ tree? Raise your hands for those who've seen B+ trees. Okay, and those who have not seen them. Okay, I'm right, it's about half. So here's just a question. So how many of you, for those of you who have not seen it, did you primarily take 302 and 140 from Planck or from Gregor? Planck? Pardon? Right, but our B trees are not B trees. This is a totally different beast. So I'm just curious. So Gregor covers it and Planck does it. Is that roughly right, or is that not right? No, Planck covers it too? And you didn't see it? Okay. Just curious. Okay, Planck did it in a special topics class. Okay. So at any rate, I'll be going over it. Same thing with extendable hashing. How many of you seen extendable hashing? There we draw a big 0. Okay. Okay. So basically, B-plus trees are a generalization of binary search trees. And extendable hash tables are generalizations of hash tables. Okay, we'll get into them probably primarily next time. But binary search trees and regular hash tables stink when it comes to external organization. If you were to use binary search trees or red-black trees or splay trees or AVL trees or regular hash tables to store files, your performance would be horrible. Okay? I'll explain why when we get to them. So we store things in these 3 types of files, and we can organize a file on what's called a cluster key. Okay? A cluster key is simply the field or fields on which we choose to organize a file. We often do not use the primary key. Okay? The reason we typically don't use the primary key as the cluster key is that the primary key is an artificial key. And if you cluster keys, you're going to do it because it benefits a range query. So for example, in a database, I might want the list of all people whose names start with S. Okay? That I want a cluster because I want all the people who are S close to each other. Or I may want in a race database, because I used to be a runner, I might want it organized by race times. I might want the list of runners who finished a race in less than 15 minutes, or the list of runners who finished the race in more than 50 minutes. Okay? It benefits me if those records are clustered together. Why? Based on what I've just said, why is it beneficial to cluster those records rather than having them all over? Gabriel. You have to read fewer blocks. Okay, if all my race times that are under 15 minutes are clustered together, let's say there's 200 of them. Okay, and remember, let's say there's 40 tuples per block. Okay, it's going to be roughly 5 blocks. Now there's going to be slop, right? Some of them are going to fall. It's not going to be exactly 5 blocks, because maybe this is 40, 40, 40, this could be 20, this could be 30. So it might be an extra block down here. So you might really have 6, right? But roughly speaking, you have 5 to 6 blocks, whereas if they're scattered throughout the database, you might, going back to my example, I said if there's 100 blocks, you'd be reading 100 blocks rather than the 5 or 6 that you could do if they were clustered. Okay? Now, if I had clustered the runners according to their runner ID, which is pretty meaningless, right? It doesn't have any real meaning. I can be pretty sure they're going to be scattered all over my database. So that's why we typically don't cluster on a primary key. Kind of interesting, right? Because the primary key uniquely identifies the tuple, and yet it's rare that we cluster on the primary key. So that's something that you should realize. Now, there is a difference in terminology. So we use indices as a way to speed up our access times. Okay, and it's adopted from index in a book, right? If I want to find some chapter that I really loved in a very long book, let's say Lord of the Rings. Good Lord, that thing's long. I have no idea how many chapters. Let's say it has 80 chapters. Okay? And you want to find where chapter 56 begins, you go to the table of contents, right? That's an index. That gives you a very fast way to find the page number where chapter 56 begins. Otherwise, you sit there kind of leafing through the book trying to find where chapter 56 is. So that's the idea of an index in a database system. The idea is you have an index. Let's say you have salary. Okay, so you might have salaries that are 10,000, and it points to all the different places. So this is my conceptually where all my records are stored. You can think of them conceptually as being in a big long array, even though they're not. Then I might have those that are 15,000. It might go to certain other ones. So they're essentially pointers to disk addresses. And we're not going to be too worried about what those disk addresses are. They probably are going to at least contain a disk number, because remember they're platters. So it probably would have a disk number, a track number, and a block number at the very least. So probably at least 3 pieces of information associated with a disk address, but I'm not going to go into that. I'm not an expert on file systems, so if they use a different addressing mechanism, I'm not going to worry about it. But there is the disk analog of a pointer. Okay, so an index contains a key value and a disk analog of a pointer. And that allows you, once you have the appropriate entry, like if I'm looking for all people making 15,000, once I am at that entry, it will take one disk access to get each of, in fact, these two are together, so I can probably get these two with one. This might be a separate one, and this one might be a separate one. Okay? And a query optimizer is not going to be dumb. A query optimizer, when it figures out what the disk addresses are, it's going to eliminate duplicates. So when it finds out that these two are the same disk address, it's going to eliminate duplicates. It's not going to be so stupid as to read the same block twice. Okay? So we set up indices to make our disk accesses more efficient. So first of all, there's 3 kinds of indexes. There's a primary index, a cluster index, and a secondary index. Primary index is an index where the file is physically clustered using the primary key. Maybe for some reason it turns out that names are unique. So we end up using the name as both the primary key and the cluster key. That makes it a primary index. A cluster index is one where the file is physically clustered on a key other than the primary key. So for example, if I clustered my race database on race times rather than on racer IDs, then that would be a cluster index. The cluster index would be on the race times. And then a secondary index is an index on any non-clustered attribute. Okay, so it could be on, for example, the racer's name, maybe the racer's zip code, things like that. Okay, so remember what the terminology is for those 3 types of indices. And if you're clever, you can sometimes solve a query just by looking at the index rather than by looking at the relation itself, and that most often happens with aggregate queries. So for example, if I said select average salary, there's no reason to read all the tuples in the relation if I already have an index on salary, because I can simply go through the salary index and compute the average salary. That also can be used to give me the minimum salary and the maximum salary. Actually, it can also be used to give me a count of the salary. So you can use, or the query optimizer can use indices sometimes to answer a query without actually having to go out to the file itself to retrieve the tuples in the relation. And you might wonder, where are the indices stored? We will see as we get to them exactly what's going on there. The short answer is part of the index, well, the entire index is also stored on disk. So when you're accessing the index, you're also making a disk access. Now, typically, some parts of the index are cached in memory to make some accesses faster. So in reality, as the database is operating, some parts of the index are cached in memory and other parts require disk accesses. Okay, again, query optimizers are trying to make some intelligent decisions about that. Okay, so questions thus far. Okay, so you might think that if we're going to choose indices, you might think, well, why don't we just index everything? Because clearly, disk accesses are expensive, and we don't want to have to read through the entire relation or through the entire file containing the relation. But indices have costs. We have to maintain them. If we insert a new tuple or delete a tuple or update a tuple, we have to update the indices. Okay, if we have 10 attributes and 10 indices, we could end up having 10 different disk accesses to update each of the 10 indices. So indexes are not panaceas. Also, indexes aren't necessarily just on a single attribute. They could be on multiple attributes. Okay, like in the hotel study where we had the room relation, the primary key was hotel number and room number. So the index there might actually be hotel number and room number. So indices can also be on multiple attributes, not just a single attribute. Okay, so if we are choosing indices, things that we typically index are the primary key of a relation. Okay, now as I said, oftentimes the primary key is not the cluster key. So oftentimes the primary key is what kind of index? If it's not a cluster, if it's not the primary index, it is secondary. Yes. And the reason that we typically index the primary key is that primary keys are involved in joins. Joins are one of the most frequent operations in a database. Therefore, it is a good idea to have them be indexed. Okay? Same thing with foreign keys. Foreign keys are typically used in joins, and therefore it tends to be efficient to join on, or in performing a join, to be able to find the foreign key efficiently. Okay, so for example, we might have select, let's say we want all students the names of all students who are taking CS 465. And remember, we had, from earlier in the course, we had a student relation, we had student courses. So it might be select student name from student courses where let's call this S and this SC, so I don't have to calling this SC and this S, so I don't have to sit there and write them out. So where SC dot course ID equals CS 465 and student, or S, sorry, S dot student ID equals student course dot student ID. Okay, so what's going to happen is we're going to, first of all, probably what the query optimizer is going to do is it's first going to find all the records where the course ID is equal to 465. So then it's going to have a list of records where the course ID is 465. And for each course ID, there's a student ID in there. Okay? If we don't have a secondary key on student ID, the only way we can now do the join with student is to essentially scan through the entire student relation looking for S10, S12, S15, etc. Right? In fact, probably what we would do, we're actually really toast. Why are we really toast if we don't have an index on student ID? And if the most likely, what is the student relation? What most likely is it clustered on? Student ID? Think? How about name? Yeah, probably name. Okay, so the student IDs are randomly distributed through the student file, right? Okay, well, think back to like 302. How are we going to be efficiently, even if these names, S10, S12, S15 are in order, how are we going to be able to efficiently locate the name, those IDs in the student relation? We can't, right? All we can do is basically read every single block from the student relation, and then for each record here, check to see if any of those IDs are in that block. Okay, whereas if we have a secondary index on student ID, then we can limit our accesses to only those blocks containing student IDs that we're interested in. That's why we're typically indexing foreign keys and primary keys. Even if it doesn't look like we're doing any kind of selection query on them. So the selection query here was on course ID, okay, which in fact, in some sense, is a primary key. But we're not doing any kind of selection query there on student ID. Yet, as you saw, it turned out to be highly beneficial to have an index on student ID. Okay? So we typically index primary keys and foreign keys. Okay? C, we add a secondary index to any attribute heavily used in selection queries. Okay? So and we'll get to this in a moment, which queries to analyze, but if some attribute is coming up often, now this right here was actually a primary key for the student courses. Actually, it wasn't. It was a foreign key, but it was already indexed. But something like salary, let's say if we're doing a lot of queries on salary, or maybe on GPA, then those would be attributes that we also might choose to add a secondary index. So even though they're not ever used in a join, only primary keys and foreign keys are used in joins, there are certain other attributes that we're frequently looking at. Okay, in the Dream Home database, probably a common query is people looking for properties that have 3 or more bedrooms, or properties whose rent is between 500 and 800, or less than 500. That is, a lot of queries are going to be based on rent, and a lot of other queries are going to be based on number of bedrooms or number of bathrooms. So those two attributes, number of rooms or number of bedrooms, number of bathrooms, rent, are probably going to be things we want to put a secondary index on. Okay? If we're frequently doing aggregate queries on certain attributes, we would tend to order by that. Now, turns out, oftentimes the order by and group by attributes are going to be the same as your primary and foreign keys. Not always, but frequently. Like, think back to the average, well, that's not quite true. You're going to order by, okay, your order by, that's not true, sorry. Back up one more time. Your group by attributes are frequently going to be primary keys or foreign keys. So for example, if we want to calculate the average salary by branch, okay, the group by attribute is going to be branch ID. Okay, if we want to calculate the average revenue per hotel, it's going to be, group by is going to be on hotel ID. So group by is going to frequently be a primary or foreign key. Order by is infrequently a primary key. Why is order by unlikely to be a primary key? Yes, Gabriel.
Is it because primary keys are artificial?
Right, they're artificial and therefore meaningless. Okay, typically we want to order by something more meaningful like last name and then first name or salary or race time. Ordering by an artificial key doesn't really help in a report. Okay, when I get my Scantron forms back in CS 102, I could care less what the student ID is. If they give me sorted on student ID, it's worthless. Whereas if they give it to me on the last name, it's valuable because then I can enter it easily into Blackboard. Okay, same thing. When in Blackboard, I want to look at things organized by last name, not by your student ID. Okay, Gabriel, if you send me a query, it doesn't do me any good to know your student ID. I need to know your last name. Okay, so order by tends to be on an attribute that is not the primary key or a foreign key. And aggregate functions are not going to be typically on foreign keys or primary keys. Okay, they're typically going to be on things like race time, salary, gender. Okay, it's not very frequent that you're going to do any kind of aggregate operation on a primary key or a foreign key. So if you're often sorting on an attribute or if you are doing an aggregate operation on something, and that's what it meant by the built-in functions here. That is a synonym for aggregate functions. Okay, a better word there would be aggregate functions. Okay, by the way, the order by is frequently this set and this set are probably going to have a high intersection. Those are probably going to have a lot in common. If I'm asking to look at salaries, there's a good chance I'm ordering my result on salary. If I'm looking for people, there's a good chance I'm ordering it on people. So there's a good chance that C and D1 have a high overlap. Okay, E and F also have a high overlap. Okay, the attributes involved in aggregate functions are also the ones that often can be solved using an index-only plan. So salary is often used in an aggregate function. It can often be solved just by looking at the index. Okay, so you're thinking, great. And remember, sometimes an index will be on multiple attributes, not just a single attribute. Okay. Okay, so clearing that. So there are also things that you tend not to index. Small relations. Okay, so if I am talking about the number of departments in the university, there may be, say, 80 departments. That may seem like a lot. Not when you store it in a block that can contain 40 departments. That would be a 2-block file. Okay? An index is not going to save you any time. Why? Because an index will take usually 1 disk access, and all that index can do is your relation had 2 blocks, right? At most, you are ever going to read 2 blocks. So an index is going to already cost you 1 block access, and then you're still going to have to read at least 1 of the 2 blocks from the relation. There's no win there. There is a loss because every time I update a department's name or delete a department or add a department, I have to update the index. All I'm doing is slowing down my system by indexing small relations. Okay? This one is one that's hard to evaluate, but if you're updating an attribute real frequently, it's going to cost a lot to maintain it in the index. Good example, if you're Amazon, what attribute probably changes a lot? Number of items. Okay? Not just that, well, you do, but here's the problem, right? When is it important to have queries on number of items? Yeah. If you probably want to have a run at certain points in the day that says if the number of items is less than some threshold, restock. Okay, so there's tension here. That's a pretty common query to want to know the number of items that are less than some threshold. But on the other hand, the number of items is being constantly updated. Okay? Well, there's a trade-off here. How many times are we likely to run that query on the number of items? A couple times a day. Okay? How many times is the number of items being updated? If you're Amazon, thousands of times a day. Okay? So probably you don't index number of items. Instead, you just do a scan through your inventory and you take the hit. So it's a matter of figuring out which query is going to happen more often. In this case, you're going to be updating the index far more often than you're going to be asking for the number of items. So you have to be kind of aware of what the trade-offs are. Okay? Another one to consider is sometimes an attribute could be heavily used in a selection, but it's not really going to help you because the results are going to be so big or so scattered that you're going to end up retrieving most of the blocks in the database anyhow. Okay? Think again about number of items. Okay? We're not clustering our inventory by number of items. So the products that have, say, less than 5 items less are scattered all over the files. And if we're really doing a brisk business, we probably are restocking several times a week. What it means at any given time is we may have a fair chunk of our items below the threshold, like say 4%. So let's say at the end of any given day, we have roughly 4% of our items that need to be restocked. Okay? That doesn't seem like a big number. Okay, 4%, you're thinking that's a lot less than, so let's say that we have, let's say we have 100,000 items, and at any given day, about 4,000 of them have to be restocked. Seems like that's a lot less than 100,000, right? Except that let's say we get 40 items per, we have 40 items per tuple, or per block. What does that mean? It means on average at least one item is going to be in each block. 4% means that, so we have 40 items per block, and they're randomly scattered everywhere, okay? So if you're thinking about, how do I want to say this? Let's first start out with how many blocks we have. We have what, 250? We have 2,500? Yeah, we have 2,500 blocks. There we go. That's the way to do it. So if we have 40 items per block, we have 2,500 blocks, right? And if they're randomly distributed and we have 4,000 items, average hit rate per block is over 1, right? Come on, you all took 313, or most of you have. The expected value, the expected number of items per block is over 1, right? If they're random, they're randomly scattered, it means that we're probably going to end up retrieving most of our blocks anyhow. So even though only 4% of the items were returned in the query, that still means that almost every block in the file has to be read if it's randomly distributed. Okay? So that's another reason why we don't end up indexing the number of items. Because even if we index, it's unlikely to be worth it. So we only really want to do indices where the expected number of records per block is a lot less than 1. Okay, that happens when we do a join on our primary keys. If we're looking for the students in CS465, I know this might seem like a big number, but 90 out of 30,000 is not huge. Okay, that's what? certainly less than 1%. It is about 0.3%. Okay, that's probably going to be low enough that we are not looking at nearly every block in the database. So we only want to do a attribute on, or a index on an attribute if the expected number of records per block retrieved by the query is much less than 1. Otherwise, we're going to be pretty much reading every block in the file anyhow. Okay, does that make sense? Okay, and finally, we want to avoid indexing really long character strings. Okay. And that should be, why do you think we try to avoid it if we can? Pardon? Well, string comparisons are no good, right? And that's one good reason. Storage is a bear. If you're indexing on addresses, you could easily be up to 40 bytes. An address could easily be roughly half the space for a tuple. So that index is going to roughly increase the amount of storage by 50%. Okay? You like to index compact things. Things that are super long eat up a lot of storage. So Adam had one, but the reason, Adam, that string comparison isn't so bad is it's in the CPU, and we're willing to trade inefficient. So that's actually an example of we're willing to trade CPU, inefficient CPU, for fewer disk accesses. So even though string comparisons aren't efficient, we don't care, to be honest. It's more because they significantly increase storage costs. Okay, so when you're coming up with your list of, so you have to figure out, so I had these considerations in choosing indices. Okay, so you have to figure out then what are your likely queries. Okay, in advance, that's really hard to know because what you're trying to estimate is frequency of the query, not just what the query will be, but what is the frequency of the query, right? I just showed you that with the number of items remaining. You have to estimate how many times that you're adjusting the number of items versus how many times you need to know how many items are left. Okay? So guessing the frequency in advance is not easy. All you can do is what are called back-of-the-envelope calculations. I expect the number of updates to num items to be high, whereas I don't think I will frequently be doing a query that asks to return the number of items less than 5. Now here's a question. It does seem that number of items gets updated a lot, right? Not the index, but number of items is often updated, right? Every time someone buys something, we have to decrease the count by 1. We agree with that? Well, that seems like we would want to index it then, because all the time we need access to that tuple in order to update the number of items. What's the fallacy in that argument? Seems like we need an index on num items to get to the tuple so we can update it. Pardon? Okay, you're right, you'd have to update the index, but I guess what I'm looking for is, it's hard to describe. You already probably have the tuple in hand. Before someone buys it, they want to know the price, right? They want to know its description. They want a picture. So you have that tuple already. It's already in memory. You got it on another query. When the user said, give me all cooking pans of this type, like skillets, you already retrieved the tuples. They're already in memory. Therefore, it's not any big deal to update the number of items. You don't have to execute another query to get at it. It's there. That's why. So, but I'm trying to give you an idea of why this is complicated, right? You have to be able to think through all these scenarios. You realize number of items is going to be frequently updated. Oh, maybe I should put, I shouldn't put an index on it. Oh, but I need the tuple in order to update it, so is it really that bad? Wait a minute, I already have the tuple in memory. I don't need the query to do it. So it's first level, second level, third level. It's a whole chain of deductions. At any rate, what I've found is you try to just analyze the queries you think are going to happen the most frequently, and then you implement it, and then you tune it. A lot of tuning comes after the database is up and running. And then you keep logs. You figure out what queries are happening a lot, which ones are slow. Okay, you can get that from your log information. And based on that, you can adjust your index strategy. Okay? So it's all squishy. You know, there's no hard and fast things, but that's why I gave you the list of things to do and things not to do. There is a homework problem on it, but what I really expect you to know for a test is the general principles of what's going on, not I'm not going to, on a test, say, here's a relation, tell me what you're going to index and what you're not going to index. I'm much more likely to ask you a question such as multiple answer, which of the following things should you frequently index? And I'll give you a list of things, and you should circle the things like I'll say, primary key, foreign key, small relation, okay, long character strings. And you should only circle foreign keys and primary keys, because I told you small relations and long character strings should not be indexed. So that's the more likely question I'm going to ask. Okay, so got about 5 minutes, and not going to start into B+ trees or extendable hashing today. I'm going to do that on next Tuesday, but couple things. First of all, I did, if you look here, the chapter 18 of the book doesn't really talk about B+ trees and extendable hashing. Their appendix F is online, and depending on whether or not you anteed up for the book, you may or may not get access to appendix F. Okay? But I did, there's a book that I really like, by, I can't think of his first name, Weiss. We used to use it in 302. So what I did was I copied his 2 sections on extendable hashing and B+ trees, and I put them into Blackboard. So if you go to Blackboard and you look at course materials, you can get PDF files for B+ trees and extendable hashing. It would be good if you look at those 2 handouts before you come to class on Tuesday, because I'm going to move quickly and this stuff is a little hard to follow at times. Okay, but it's only worth spending a day on it. I'm going to try to cover 2 data structures in a single day. So I would take a look at that before you come to class on Tuesday. Second thing, we have a midterm coming up a week from Tuesday. No, it's a little early, but just to give you an idea, I haven't made it up yet, but there's likely to be some multiple choice / multiple answers. There's likely to be a question that asks you to do a query or 2 for SQL, relational algebra, and relational calculus, because those are the 3 query languages we discussed. Okay? It's going to be, the queries would be on the direct manipulation language. I'm not going to get into the DDL in a problem. On the multiple choice, multiple answer, that's where I would hit you with the DDL. So the queries would be things like, not this simple, but give me a query to select all employees whose salary is less than $50,000. Okay, and I might say, give me the SQL version of that, the relational algebra version, and the relational calculus version of that. Okay, then there's likely to be a problem that involves drawing an ER diagram for me. And there's possibly a problem that involves doing normalization. There will not be a question on extendable hashing or B+ trees until the final. That is because you will not have had an opportunity to work the homework assignment and get your grade back. There will be questions on physical design, what I went over today, because those will all be multiple answer, multiple choice. Okay? I certainly don't see any unfairness in asking you to regurgitate for me what rotational latency is, or what seek time is, okay? Or what a transfer rate is. Okay? You can memorize that. Okay? There will be no cheat sheets for this exam. So it's going to be multiple choice, multiple answer, and if there are problems that you fill in, work out, it will be for queries, for ER diagrams, and for normalization. There may not be a problem for each of those three. You'll notice that I managed in the quizzes to come up with questions for normalization in particular that didn't require me to have you write something out. So it's much more likely that I'll have you do an ER diagram and queries than I would normalization, but you need to be prepared to do all three. Okay? Yes, Beth?
I thought you had mentioned earlier there would be a cheat sheet.
If I did, the answer is no. Because I also, okay, in the past I had to, here's the difference. In the past, this class was small enough that I didn't have to resort to multiple choice. Okay? This class is so large, I have to resort in part to multiple choice, and cheat sheets defeat the purpose of multiple choice. Okay? So I'm sorry, but the only thing where a cheat sheet's really going to help you is on some of the SQL queries, and I will be a little bit lenient if your syntax is not exact. Okay? But I'm not also going to ask you really, I'm not going to say, show me a aggregate query where the count is greater than 10. That's, I consider esoteric. It's going to be the meat and potatoes. I'm going to be expecting you to know how to do a join. Okay? So that's the other, I'm going to expect you to know meat and potato stuff on those problems, not the esoteric stuff. The esoteric stuff you can recognize. So there's a difference between what psychologists call recognition memory, being able to recognize something, and being able to recall something. Multiple choice is recognition. You just have to recognize this is what an aggregate query looks like. Whereas recall means you have to recall from memory what the syntax is. Okay, so on the problems which are going to require recall memory is going to be meat and potatoes. Okay, the multiple choice is where the other stuff is a little more esoteric, but there you can recognize it. So no cheat sheet. Okay, that's still a week from Tuesday, but today marked where the material cuts off for the exam. Okay, so the material for Tuesday on B-trees and extendable hashing will appear on the final. And the next Thursday, we actually start into scripting languages. Okay, and then we have the test a week from Tuesday. So I will see you all on Tuesday. Remember, you have an exam, homework due today, and also I have a 5 o'clock flight, which means I'm leaving now. So I'm sorry, no office hours today. I'll try to answer email, especially at the airport,